So let's move on. We'll look at the yield power law, or the Hurschel-Bulkely model. Now this describes the rheological behaviour of drilling muds more accurately than either of the other two models, and I'll explain why. I mean, if you look at the equation, you can almost begin to see why already. We've got tau equals tau 0 plus k times gamma to the power of n. Now if you look at this part of it, we've got k times gamma to the power of n. That is pretty much the power law. Adding tau 0, if you remember the Bingham plastic model had yield point plus PV times gamma. So we've got a yield point, and we've also got the benefits of the power law in that it's describing a curve. So it's describing a curve, it's describing a fluid that has a non-Newtonian behaviour, and it's also describing a fluid, giving the option of describing a fluid which has a yield point, which needs to have a certain shear stress applied before a shear rate results from that shear stress. So tau is basically the measured shear stress in pounds per 100 square feet. Tau 0 is fluid yield stress, which is the shear stress at the zero shear rate, which is again in pounds per 100 square feet. K is a consistency index, N is a flow index, and gamma is the shear rate in per seconds again. So gamma is shear rate. So you've got shear stress equals the fluid yield stress, which is the shear stress at the zero shear rate, plus K, which is your consistency index, or the thickness of the fluid, times the shear rate to the power of n, which is your flow index, or how non-Newtonian the fluid is. So have a look at that graphically. Here we've got the same equation I just explained there, and this is the sort of curve you end up with. Something that starts off, here, intersecting the y-axis at something higher than the origin due to this tau 0 value here. Now if tau 0 was 0, it would start off at the origin, so that would be fine as well. It would also describe a pure power law fluid. Now k in this is actually describing the slope of the line. K actually changes because you're using a variety of different, n and k change throughout the model. That's one of the beauties of this model. And you actually input 6 rheological values, and it will change n and k, producing a curve for the annulus and up through into the pipe flow regime as well, flow area as well. But k basically, put simply, determines the slope of the line. And n here describes the degree of non-Newtonian behaviour. If n equals 1, then it's a straight line. It's a straight line, in this case it's pretty much parallel to the Newtonian fluid line, but tau 0 being greater than 0 shifts that line up a little bit. So it's got a yield point. So it's a Newtonian fluid. It's similar to a Newtonian fluid, but there is a yield point. Now if you decrease n slightly, then this becomes more curved, and it just keeps curving off until you end up with, as n decreases, this becomes more and more curved off the straight line, basically. So the equation's similar to both the previous equations combined. That's not to say that it was derived from both the previous equations. In actual fact, what you could say is the previous equations were approximations of this equation, which fully describes a fluid. Now it's basically the beauty of it is it's got a power law relationship which describes the degree of non-Newtonian behaviour, and it also has a yield point, which is tau 0. And the yield power law is actually the law which properly describes fluids. The other two are simply derivatives of this one, and they're used to describe specific cases. Now, just to demonstrate that graphically, when n equals 1, the yield power law becomes the Bingham plastic model. So if I actually make n equal 1, gamma to the power of 1 is just gamma. So you take that 1 out of there, you've got tau equals yp plus pv times gamma. That is the Bingham plastic model. So this describes a Bingham plastic fluid. So if you're pumping toothpaste, this would describe it. It also describes a power law fluid, as in it will go through the origin. If tau 0 actually equals 0 and there is no yield point, then this becomes the power law. It becomes basically tau equals 0 plus k times gamma to the power of n. So tau equals k times gamma to the power of n. That is the power law. So it's able to describe a power law fluid. So it can describe a Bingham plastic fluid, it can describe a power law fluid, it could obviously then describe a Newtonian fluid, but the thing is it can also describe everything between a power law fluid and a Bingham plastic fluid. So it's able to cover every opportunity, basically. It's able to cover all the bases. So the model has all the advantages of both, and it also has the advantage that it can describe all the fluids which the other fluids can't describe. And another advantage over the power law is that n and k aren't actually just static numbers based on the 300 and the 600 dial readings. They're actually based on 6 rheometer speeds. It can actually be done with 3 rheometer speeds. You can reduce it and just actually use 3 speeds from the rheometer, but you're actually recommended to use all 6 rheometer speeds that you can get on a mud report these days. On most mud reports everywhere in the world, you should be able to get 6 rheometer speeds and put them into your Bingham plastic, into your hurschel bulkely model. And the model has an effective YP, as I said, which is tau 0, which is more accurate when compared to reality. And it therefore has the benefits of more accurately modelling the annular and the internal pipe flow. And the values from experience appear to lie between Bingham and power law. So when I say from experience, the values from my experience appear to lie between Bingham and power law. When I actually look at the, when I've sat and actually run through all the models with different mud types, the values you get from hurschel bulkely do tend to lie somewhere between Bingham and power law, which is why I plotted the hurschel bulkely curve in between the other two on the graph earlier. And from my experience as well, looking at actual PWD data, when you've got a very clean mud, before you actually start drilling, before there's any cuttings in that mud, if you've got a clean mud and you start pumping it, then hurschel bulkely will actually be very, very close to reality, very close to that PWD reading for a clean mud. And the other two models won't. Basically, when I say PWD reading, your annular pressure reading, hurschel bulkely does model the annulus very, very well. If it isn't in your case, if for some reason you're not getting, the model isn't describing reality very well, then I would suggest it's not because you should be using Bingham or you should be using power law. You shouldn't be using either of those at all. You should continue to use hurschel bulkely. But I would actually look at some of the inputs that you put in. Usually it's a geometry thing or something like that that's causing a difference between reality and the model's prediction. However, there are also some other things like temperature and pressure effects which can cause a difference as well.